So I've got a 9-volt battery here, and right now nothing is happening. It's loaded up with zinc metal and manganese oxide, along with a lot of electrolytes. And it's ready to have the electrons transfer from the zinc metal to oxidize the zinc into Zn2+, over to the manganese oxide to reduce it into a hydroxide compound. And it's not happening yet because there's no pathway for these electrons produced by the zinc side to get to the manganese side. So your job to use a battery is to get electrons from one side to another. Now, the most obvious solution would just be to hook the two sides to each other. But you'd have a couple problems. First of all, that would just be a waste of chemicals. It wouldn't do anything productive. But second of all, as this reaction is happening, this is a 9-volt battery, and that means 9 joules per coulomb of charge are released. So for every coulomb of charge flowing through the circuit, 9 joules is produced. So what happens to that energy? If you were just to hook the two terminals together, it honestly would just heat the battery up and it would explode. So in order to use this electrical energy to release it, we've got to have something that does work, something that takes the energy being released. So let's look at a typical something. A light bulb. So we'll zoom in on the light bulb. I think here you could see all the important parts. There's a wire that goes into it right here. And if we follow it up, it actually goes into the light bulb through the sealed base and up here. There's one on the other side that comes in and does the same thing. And they are connected with an extremely thin piece of wire called the filament. And when you hook this up to that battery, those electrons will be able to get from our zinc side to our manganese oxide side. And what will happen to that 9 joules per coulomb of charge? It will actually go into heating up that filament, making it really hot. And that'll make it glow, something called incandescence. So let's talk about how we can put this together in order to make what's known as an electric circuit. So I've got my battery, I've got a pair of light bulbs, and I've got some connector wires. And let's try to see how we can release the chemical energy stored in this battery by linking the reaction that produces electrons, the oxidation of zinc, to the reaction that consumes electrons, the reduction of manganese oxide. Now, we need to have some way to get the electrons made here to the other side where they're consumed. And we're going to do that through an electronic device which will use up the energy that's released by those chemical reactions. So I've got 2 light bulbs here. Try not to get hung up on the fact there's 2. This 9-volt, 9 joule per coulomb battery, those charges are carrying enough energy to destroy an individual light bulb. So putting the second one in just means I won't burn it out. We'll go through the physics of that later. Let's see what it takes to make this work. So first things first, I'm going to take the place where electrons are being made, the negative side. I'm going to hook up the black wire, which is the standard color for negative, and I'm going to hook it to one side of my pair of light bulbs. So nothing's happening. Why? Well, there's no pathway back. I guess I could be adding electrons here, but they have no reason to go here because this is already full of electrons, and nothing's being taken out over on this side yet. So if electrons try to go in, they'll find other electrons to repel them, and nothing happens. If we want something to actually take place, we've got to take electrons out of this side by giving them back to the positive side of the battery. So let's do that. We'll hook up the red wire over here, and we'll give that to the positive side, and we're getting our flow of electrons. So as this is happening, we have a lot of zinc atoms losing electrons. We have a lot of manganese oxide gaining electrons. And every coulomb of charge that flows is carrying with it 9 joules. And those joules are going in to lighting up the 2 bulbs. So there's a couple things worth noting here. The first is that 2 connections to our battery were needed. And that's true for any electric circuit. There has to be a place for the electrons to be added and a place for the electrons to be taken away. You might say, but Dowd, I've got my Chromebook charger, or my computer charger generally, and I plug this in and I only see 1 wire. But if you look at the connector you plug in, it's actually got a metal piece on the outside, and it's got a different metal piece on the inside. And if we were to snip this thing that looks like 1 wire, we'd see that there's actually 2 wires in it. So anytime you're hooking up electricity, 2 wires are involved. The other thing worth noting is that you probably don't turn things on and off by disconnecting the wires. You probably use a switch. So let's go through what a switch is. So now I've got a switch, and you can see it's actually a really simple thing. This is called a knife switch, and it's basically a piece of metal hooked up at one end to another piece of metal that can slide up and down and go into this V-shaped thing here. And that essentially makes a connection between conductors, and it's like opening and closing a drawbridge. When it's like this, there's an insulator between the 2 sides of the switch. When it's like this, it's all conductors. So let's wire a switch back into the circuit we had. So we'll do it the same way, but we'll need a couple more wires now. We'll go negative in black to one side of the switch. We'll go to the other side of the switch in red to our bulbs, and we'll go back to our positive. So nothing's happening. So there's no electrical connection, again, from the negative to the positive at the moment, because our drawbridge is open. Electrons are being added by the black wire to here, but there's nowhere for them to go, so they're being repelled back and charge isn't flowing. They can't be taken out by the rest of the circuit. But if we lower our drawbridge, it lights back up. So this is what you do when you turn on and off a light switch. You actually break an electric connection and make one. I'd like to do one more thing with our light bulb battery circuit. We know that zinc is being oxidized to zinc 2+ and manganese oxide is being reduced, and that every coulomb of charge that flows gives 9 joules of energy to light up our light bulbs. But how many coulombs of charge are flowing? And just how many electrons does this represent? Well, to figure that out, we're going to measure the electric current. So I have an ammeter here. And an ammeter measures current, which, as you know, is got the unit amperes, which really means a coulomb per second. So what I'm going to do is wire this ammeter in. We'll figure out how much current's flowing, and then we'll figure out over a period of time how many coulombs that represents, and then how many electrons. So we're going to hook up the ammeter, and it's not very hard to do. We just have to put it in what's called series with the rest of the circuit. Series is pretty easy to understand. It means that as we take our journey from the negative side of the battery back to the positive, that will pass through each element one at a time, one after another. So let me wire this together, and I think you'll see how the ammeter works and also how series works. So we'll start with the negative side of our battery, and we'll hook up a black wire, and we'll hook it to the negative side of the ammeter. So that's thing one. And then we'll go from the positive side of the ammeter to our switch. So the switch came right after the ammeter in series with it. And then we'll go from our switch to the bulbs. And then we'll go from the bulbs back to the positive side of the battery. So one after another. So just get that wire out of the way. Now obviously nothing's happening because the switch is open, but let's close it and observe. So the bulbs light up and the needle on the ammeter moves. Let's investigate closer to see what's going on. So if we zoom in, we can see the needles on the second major division, if we go by the top scale, which I hooked it up to, between 0 and 0.25. So that means each major division is 0.05, and this meter is currently telling us that we have 0.1 amps. 0.1 coulombs per second. So what we're going to do next is we're going to see how many coulombs and how many electrons that represents over a certain time period. Let's count off about 10 seconds. So I'll say go and then stop, and we'll watch these beautiful bulbs in their light, and we'll think about how many coulombs and electrons the light over this period represents. So go. Stop. Let's try to figure that out. Remember, in each second, we got 0.1 coulombs. So in that 10 seconds we spent watching the light bulbs, I wanted to figure out how many coulombs of charge flowed through the circuit and what that represented in terms of numbers of electrons. So our ammeter told us we had 0.1 amps, which is the same as 0.1 coulombs per second. And since we waited 10 seconds, that means we got a coulomb of charge. So what does that mean in terms of the number of electrons? Well, since we know the charge on an electron, we can divide a coulomb by that, and that gives us 6.25 times 10 to the 18th electrons, which out of scientific notation is that number. And I just think that's really cool to look at. I just think that for something as simple as lighting up a bulb, that many particles are doing our bidding for us. It just gives us some perspective on all the modern miracles we have of technology and science. We're harnessing so many small particles in order for something to happen. And it's important to appreciate that and be amazed by that, I think. I did one other calculation to try to put the amount of energy we used in those 10 seconds in perspective. I recognize this is a 9-volt battery, which means each coulomb got 9 joules. Since we had 1 coulomb, we got 9 joules total. And I thought we would take a look at that in terms of potential energy. How high would I have to lift this 100-gram mass in order to get 9 joules? And it turns out not very high, 0.92 centimeters. So I'm going to do the work on this mass required to light the bulb for those 10 seconds. And I'll take 10 seconds to do it, so I'll be outputting power at the same rate that our little battery here was. All right, so my battery's running. You can see the light bulb's lit up, and it is outputting 9 joules every 10 seconds. And I'm going to do the same thing. I'm going to give this little weight 9 joules of potential energy, and I'll take exactly the same time, 10 seconds. So we'll both be giving it the same energy with the same power. So we're both, I guess, 0.9 watts. So here we go. Starting now. There we go. That's 9 joules in 10 seconds for both me and the battery.